So counterfeit drugs often contain toxic substances or no active ingredient, and as such they are completely ineffective against disease. They may also promote pathogen resistance, and this reduces the effective lifespan of the drug and also drives up R&D expenditure. These counterfeits make up 10% of the global market, and this share is increasing, and they cost the industry $100 billion each year. Worse still, counterfeits are responsible for 1 million deaths. In China, for example, a recent study showed that 75% of cancer drugs bought online contain no active ingredient. So the pharma industry have almost no defense against this problem. They currently use package technologies such as inks, dyes, and barcodes, but with Nucleotrace technology, we actually incorporate all this product information into the tablet, and that makes counterfeiting virtually impossible. So how does it work? First, we encode product information into fragments of synthetic DNA. This may include the batch number, expiry date, and manufacturing facility, for example. The encoded DNA fragments are incorporated into the product ingredients of the manufacturing facility, and this gives each tablet a non-toxic molecular fingerprint. Samples may be recovered and decoded at any point in the supply chain, and what is more, we can process possibly up to 200 samples simultaneously in under 2 hours. So DNA is ideal for this purpose because it's safe, it's in absolutely everything we eat, it's inexpensive, and it's information dense. And on this last point, I thought it would be worth just briefly trying to calculate how much the entire 16 zettabyte digital universe weighs in DNA. So DNA is a polymer made up of 4 base pairs, A, C, T, and G. And if you map A to the binary bits 0, 0, and C to 0, 1, and so on, you can get a quick estimate of the digital universe in DNA. It comes out just 33.8 grams. So to encode a byte of non-biological information, you use the 4 base pairs instead of the 2 binary bits. In this picture, the vertical blocks represent a byte, and they're connected together to form a code word, in this case of length L equals 6, so 6 letters. The yellow nucleotides or yellow base pairs encode the data, whilst the white base pairs give error detection and correction capabilities. But this is actually a very simplified encoding system I've shown here, and an ideal system would include a number of other factors. We've been working in close communication with pharmaceuticals regulators to develop a beyond compliance encoding system that also incorporates biochemical constraints, advanced error detection and correction capabilities, including insertion, deletion, substitution errors, and also to preemptively and conservatively address any safety concerns. And so on the matter of this, we can consider dose. We actually use 100 million times less DNA and gets a therapeutic response. Specificity, the new encoding system ensures against any complementarity of the human genome, and in fact any animal's genome, and also ensures against sequences that may theoretically elicit an immune response. So a lot of advances in technology have made our tech possible, and probably the most important one is the massive reduction in the cost of DNA sequencing. 15 years ago, it cost about $100 million to sequence your genome and took many months. Today, we can do it on this device here, overnight, for about $500 to $1,000, and that's what I've designed our system for, this device. So briefly to summarize the advantages, unlike package technologies, our tech is highly secure, it's integrated into the product. Unlike advanced chemical analyses, it's low cost, offers decentralized sampling, rapid parallel sample processing, and supply chain information on each ingredient in the product. But just quickly before I go, I'm going to just touch on the application I started with, and that's ammunition fingerprinting. And the actual premise of this is actually really quite straightforward. It's because a bullet is always in contact with the victim of gun crime and provides the best means to transfer information to a crime scene. And so we could, with Nucleotrace tagged ammunition, we could routinely recover an unbroken chain of identification on the gun, the shooter, the cases, but most importantly, the victim's bullet entry wound and recovered bullet after firing. And so that allows you to recover a history of ammunition previously used in the gun. It allows you to identify a suspect from a bullet entry wound alone, and also allows you to trace 3D printed gun crime. And we can do all that in about 1 to 2 hours of arriving at a crime scene.